Okay, good morning, everyone. Let's get started. Right. So today is lecture number 7. We are going to talk the last two components, major component of concrete, water and aggregates. Okay. So far we have discussed the cement and hydration of cement. We discussed chemical admixtures. We also discussed mineral admixtures. Okay. Water and aggregate take the majority of the volume and also weight of concrete. Okay. Okay. As we can see, the major 5 components in concrete is cement, water, aggregate, mineral admixtures, and chemical admixtures. Okay. Not all concrete has admixtures such as flash or superplasticizer, but all kinds of concrete has cement, water, and aggregates, okay, including the smaller sand and larger coarse aggregate. All right, so here shows the typical volume percentage of normal concrete. Cement is around 15% plus minus, water around 20%, depending, of course, the water to cement ratio. For sand and coarse aggregate, they take around 60 to 80% of the total volume. Okay, so aggregate take majority of the volume of concrete. That's for some reason. Okay. Admixtures, not so much, especially for chemical admixtures, only like a couple of percent by the mass of cement, such as superplasticizer, air entraining agent, accelerator and retarder. Silica film and flash, these are mineral admixtures. Depending on the application, they take around 5 to 40% of cement. Okay, so we discussed this in previous lecture already. All right, so let's look at water first.
Water from any source of domestic supply may be used as mixing water for making concrete. In general, almost any natural water that is drinkable and has no pronounced odor or taste can be used. However, there are waters that may not be fit for drinking that can still be used as mixing water for making concrete. Water of questionable quality can be used if 2-inch mortar cubes made with it have 7-day strengths equal to at least 90% of the strength of companion specimens made with drinkable or distilled water. In addition, time of set tests should be made to ensure that impurities in the mixing water do not adversely shorten or extend the setting time of the cement.
All right, basically for water is very simple. If the water is drinkable, such as the tap water, it can be used for concrete. The reason is because drinkable water has not many salts in the concrete. So we worry about these different type of salts. For example, seawater has a lot of different type of salts which may affect the strength and also setting time of concrete, and we need to check that. Okay. But if the water is not drinkable, it may still be able to use in concrete, but we need to do some extra tests. Okay. So here are some of the limits for salts, organic matter, and suspensions. All right, so the table here shows us what are the tolerable levels for different type of impurities. Okay, this is the maximum concentration in ppm, parts per minute. Okay, and also why these impurities should be limited, because some of them may change the strength, may increase early age strength but reduces final strength, change the setting time, okay, and so forth. If we can do a chemical analysis of the water. Okay, we can base on this limitation and to check the water. We can also do a simple test for compressive strength. Okay, we make the concrete a mortar sample with the water which is in question, and we check the strength for the minimum percentage of the control mix at 7 days. The concrete sample with the questionable water should be has at least 90% of the 7-day strength of the control mix. Okay, and for setting time, the difference from the control mix should be within 1 hour early to 1.5 hours later. Okay, within this range, the water can be used. Okay. So, and we have either ASTM standard or H2 standard to follow for this test. Okay, so very simple. Then let's look at aggregate. Aggregate, first of all, should be an inert failure, which means there should not be any chemical reaction between the sand and the coarse aggregate with cement and water. Okay, so it should be inert, but that's not always the case. If there's chemical reaction between the aggregates and other components in concrete, we may have some problems, such as alkali reaction. Okay, we're going to talk about this more when we talk about durability issues of concrete. So aggregate should increase dimensional stability. So aggregate should not expand or shrink. Cement paste, on the other hand, they may shrink or expand due to chemical reaction or shrinkage. Okay. So aggregate should increase stiffness, toughness, and also wear resistance of concrete. They take about 70% plus or minus of the total concrete volume. The cost of aggregate is much cheaper compared with cement. So we can see only 5 to 10% of the cost of cement. Okay. Aggregate should affect the fresh property of concrete, such as the slump of concrete, strongly. Okay. And also hardened properties, because the strength of aggregate will also affect the strength of concrete. Okay. But it should not affect the chemical reaction, the hydration of cement at all. The shape of aggregate is also important. We should avoid flat or elongated shape for the aggregate, because that will reduce the slump, make the concrete harder to mix. Right, so this is another table summarize the property of the concrete affected by the property of aggregate. Okay, so the column on the left showing us the property of concrete, such as the resistance of concrete to freeze and thawing, resist to heat and cooling, okay, alkali reaction, or we call that alkali aggregate reaction, and what property of aggregate affect this property of concrete? For example, freeze and thaw. The soundness, porosity, pore structure, and permeability are the property of aggregate, which may affect concrete's freeze and thawing resistance. For the strength of concrete, the strength of aggregate, the surface texture, are the factors affecting strength of concrete. For shrinkage and creep of concrete, E value, or the modulus of elasticity of aggregate, the shape of aggregate grading, which is the particle size distribution of aggregate, cleanness on the surface. If we have some clay on the surface of aggregate, that may affect the bonding between the cement paste and aggregate, So in turn, that will reduce the stress of concrete. Even the size of aggregate will also affect the strength and the shrinkage of concrete. Okay. So you can just have a look of this information in this table. All right, and here shows the classification of aggregate. Depending on the size, we always say we have sand and coarse aggregate. So that is based on the difference in sizes. For sand or fine aggregate, the size is smaller than 4.975 millimeter, or we call that number 4 sieve. Okay, we know we have different sieve size. So number 4 sieve means for every inch of length on a sieve, we have 4 openings. And the clearance, the size for each opening is 4.75 millimeter, a little bit less than a quarter of 1 inch. Okay. Larger than that, we call that coarse aggregate. So coarse aggregate is the aggregate retained on the number 4 sieve. Normally, the size of coarse is less than 2 inch or 50 millimeter. And based on density, we could have heavy weight, larger than 130 pound per cubic foot. Okay. Most likely, we will use normal weight aggregate, which has a density between 95 to 105 pound per cubic foot. Okay. And sometimes we use lightweight aggregate to make lightweight concrete. This is pretty common. For example, our concrete canoe team, they will use lightweight concrete by using a different type of lightweight aggregate. Okay. The density for lightweight aggregate should be larger than 75 but less than 95. Some of them are even lighter than 75. Okay. Based on the source, we could have natural source. The basalt sand and the basalt aggregate we use in the lab, and also the mound-induced sand, which are commonly used here in Hawaii, are all natural mineral aggregates. Okay. We can also use coral sand, okay, here in Hawaii. Synthetic aggregate, we could use some of the lightweight aggregates, such as foamed slag, foamed flash, belong to the synthetic aggregate categories. We could also use waste materials, recycled materials as aggregate. Several years ago, we have a research project trying to use container glass. We crash the container glass into suitable size, and we use that in concrete. And we also check the durability of the concrete using the container glass. Okay. We could also use demolished brick or demolished concrete. Okay. We use that recycled materials, put in aggregate to reduce the cost and preserve the environment. Okay. So yeah, based on source, we have different source, but most likely we'll use natural mineral aggregates in the concrete. Okay, so that's the source. Then let's look at the packing density. Okay, the packing density is affected by gradation of aggregate or the particle size distribution of aggregate. Okay, the weight content is very important for concrete, the weight content of aggregate. The weight content will decrease when we try to combine aggregate with different sizes. Okay, so for example, in this experiment, the first one we have mono size, coarse aggregate. The size is large, but it is very similar to each other. And we need this much of water to fill the cup. So the volume of water is the total volume of the interparticle space between the coarse aggregate. Let's say we need this much of water to fill all the gaps. The next experiment, we have smaller size, but also similar size, mono size. So we also need similar size of amount of water to fill the particle size, to fill the cup. The last one, we combine small and large aggregate, and we can see we need less amount of water to fill the cup. So that means the void between the aggregate decreased. So that is a good thing, because the smaller the voids, we need less cement paste to fill the voids. So for certain amount of cement paste, the slump of concrete or workability of concrete will be increased. So we try to minimize the voids between all the aggregate. We can also see from the curve. So the curve shows us by changing the percentage of the sand, okay, what is the percentage of the voids for different type of aggregate. We have either granite, which has angular shape, or gravel, which has rounded shape. For both these two types of aggregate, when we change the percentage of the sand, we have a minimum percentage of the voids at certain percentage of the sand. Okay, so when you design a concrete, we should follow this. Okay, again, the reason is we try to minimize amount of voids, so we have more cement paste to work for the workability. Okay, we're going to talk about this more. So the paste volume and aggregate dispersion has a strong correlation. The amount of cement paste required is actually greater than volume of voids between the aggregate, which is we just discussed earlier. Why? That's the reason. Okay, that is because if we just provide enough cement paste to fill the volume of voids between the aggregate, the particle will touch each other. As a result, the concrete will be very, very hard to mix. The slump is very low. It is super hard to compact the concrete. So we need more cement paste to increase the distance between the aggregate. So the friction between the aggregate will be lower, so the concrete becomes more workable. Okay. The paste content will affect workability of concrete, the slump, cohesiveness, okay, cost. More cement paste will increase the cost, and also the shrinkage. Okay. Remember one thing: only cement paste will shrink. Aggregate will not shrink. So the more aggregate we put in the concrete, the less shrinkage the concrete will experience, which is good. Also, the cost of the concrete will also be lower because aggregate is cheaper, much cheaper compared with cement. The permeability of concrete will also be lower when we put more aggregate. That's the typical case, but not always. Okay. So the question here is how much cement paste is actually needed for a certain type of aggregate, a certain type of concrete. Let's see, we have this type of basalt aggregate. As we can see, some of them are very porous on the surface. Okay. And here shows a packed aggregate. And let's imagine we introduce more and more cement paste in a system to make a workable concrete. So initially, the cement paste is just to cover the surface of aggregate. So that's the first function of cement paste, to cover the surface of the aggregate. The smaller size, we have more surface area. We need more cement paste to cover the surface. The rougher the surface texture, we need more cement paste to cover the surface. The higher the porosity of the aggregate, we need more cement paste. Okay, so that depends on the property of aggregate. So that's the first component, the paste to cover the surface of aggregate. Then we introduce more cement paste into the system. And the second component, so our second function of the paste is to fill the interparticle space. which highlighted in the blue color here. Okay, so the pace to fill the interparticle space. So that is affected by the packing density of aggregate, which we just discussed earlier. That is depending on the gradation of aggregate. So gradation of aggregate has a strong effect on the packing density of aggregate, and that will affect the component too. Right? And we know this is not enough. We need more cement paste to make the concrete workable. So we introduce more paste into the system, which is highlighted in the green area. Okay, so we need more paste to increase the particle space. Okay, so the friction between particles will be less, so we can achieve the desired slump. Depending on the type of aggregate, where we want to use aggregate, the slump will be different. Okay, so remember, the aggregate has three functions or three components: to cover the surface, to fill the interparticle gap, and to increase particle space so we can achieve a certain slump or certain workability. So here is a video showing us what is gradation, how we can measure and calculate the grading of sand and coarse aggregate.
When selecting fine aggregate for the production of concrete, ASTM C33 also requires that the fineness modulus must not be less than 2.3 nor more than 3.1. To determine fineness modulus of an aggregate, add the cumulative percentages by weight retained on each of a specified series of sieves and divide by 100. For example, an aggregate with a cumulative percent by weight retained on each sieve of 2.8% for the number 4 sieve, 9.6% for the number 8, 31.9% for the number 16, 56.5% for the number 30, 79.7% for the number 50, and 93.9% for the number 100, has a total cumulative percent by weight retained of 274.4. Dividing by 100, the fineness modulus of this aggregate is 2.74. Fineness modulus is not a measure of the quality of an aggregate. It is an index number that is roughly proportional to the average size of the particles in a given aggregate. The lower the fineness modulus, the finer the aggregate.
All right, so this video shows us how to calculate the so-called fineness modulus. This is for sand only. Okay. Next week in the lab, we're gonna do the sieve analysis for sand and coarse aggregate. So the test for the sieve analysis is very simple. So we put all different sieves of different size together, okay, from small to large, okay, and based on the sieve analysis, we can calculate the percentage of the aggregate retained on each sieve size. Okay, so for example, we have 2% retained on number 4 sieve, 9% for number 8 sieve. Okay. Then we calculate the cumulative percentage. The so-called cumulative percentage is the percentage retained on all sieve size above. Okay, for example, for sieve number 16, the cumulative percentage is 30, which is the percent retained on number 16, 19, plus 9% retained on number 8 sieve, and plus 2% retained on number 4 sieve. So 2 plus 9 plus 19 is equal to 30. Okay, and then we add all these cumulative percentage together. We get 283 divided by 100. So the fineness modulus is 2.83. Let's talk more about grading curves. Okay, for normal concrete, the size is from 150 micrometer, which is 0.15 millimeter, to around 2 to 30 millimeter. Is around 1 inch in size. Okay. So we could have so-called well-graded aggregate. Okay. So well-graded is the gradation we design because we need less cement. We have better packing density for well-graded aggregate. The workability is also better. We could have less segregation. Aggregate will not easy to settle to bottom, okay, and the better finish concrete. We could have gap graded aggregate, which means there's no medium size, okay, which is not good. Okay. We could have segregation problems if we do not have medium size aggregate, okay, and the concrete will be more steep compared to concrete with well-graded aggregate. For some situations, we could have no fines, which has no sand. Then the density of concrete will be lower, the strength will be lower, the permeability of concrete will be higher. In situations such as pervious concrete, which is a special type of concrete, it can drain the rainwater very quickly. We could use pervious concrete in situations such as parking. Okay. In this special situation, we may use no fines in aggregate. The curve on the right is showing us recommendation bound, upper bound and lower bound from ASTM CEE375. Okay. Our normal concrete, the gradation should fall between the upper and the lower bounds. Okay, so this is ASTM gradation limits, upper and lower bound for different shape size. Okay. And this is gradation limits for coarse aggregate. The previous slide is for sand, and this is for coarse aggregate. Okay. Then let's look at the density of aggregate. The apparent specific gravity is calculated based on this equation. Okay. The volume of aggregate divided by the volume of the weight of aggregate, divided by the volume of aggregate, and over the density of water. The density of water is 62.4 pounds per cubic foot. Okay, and based on that, we can calculate the apparent specific gravity. And the volume here is the volume of the solid, black color, plus the volume of the internal voids of aggregate. Okay, but the volume does not include interparticle space. For normal aggregate, the specific gravity is around 2.4 to 2.9. For our lab aggregate, the value for the basalt and moly dune sand is around 2.6, 2.7. Okay. There's no unit for apparent specific gravity. Okay. For the bulk density, so this is defined as the weight of aggregate divided by the unit volume. So total volume. Okay. We have one of the tests in lab number 3, we measure the bulk density of coarse aggregate. Okay. Because the volume including both the internal voids, the volume of aggregate, and interparticle space. So the bulk density will be lower compared to the first one. Okay. Remember the unit volume including the solid volume, internal voids, and also volume of interparticle voids. Okay. So here shows an example of calculation. So let's say we have specific gravity of 2.6. So 2.6 means the density of aggregate is 2.6 times the density of water. Okay. So, and also we get bulk density, let's say 120 pounds per cubic foot. Okay. And based on that, we can calculate the solid volume. So 120 pounds cubic foot. So this 2 pound porous density of water times 2.6. So here in the bottom is the density of aggregate. So based on that, the solid volume is 0.74, which means for every 1 cubic foot of total volume, 0.74 cubic foot is occupied by the aggregate itself. So the void volume is 0.24, 26 or 26%. So which means the interparticle space is 26%. Okay. So that is calculation of volume. The next is moisture condition. Moisture condition is very, very important for us to design a concrete because in real situation, moisture condition of sand and coarse aggregate could be varies a lot. Okay, and we need to calculate moisture condition as accurately as possible, so we can do the mixing design. Right. So let's look at the video first.
The amount of water an aggregate will absorb depends on its porosity. The more.
Oh, sorry.
The amount of water an aggregate will absorb depends on its porosity. The more porous the aggregate, the more water it will absorb. There are 4 designated moisture conditions for aggregates. They are oven-dry aggregate, containing no moisture at all, air-dry aggregate, containing less moisture than it is capable of absorbing, saturated surface-dry aggregate, when all permeable voids in the aggregate are filled and there is no water on the exposed surface, and damp or wet aggregate, which is aggregate containing free moisture on the surface, in addition to having all the voids in the aggregate filled with water.
Yeah. So first of all, we talk, 4 moisture conditions for aggregate. Okay, we have oven dry, we have air dry, we have saturated surface dry, okay, or called SSD, okay, and wet condition. Okay. For oven dry condition, that's simple. The aggregate has no water on the surface, and no water in the permeable pores. Okay, no water whatsoever in the aggregate. We call that oven dry. So this one is easy. We also have air dry condition. The surface is dry, but the permeable pores are partially filled. As we can see here, the blue areas means water. The next one is saturated surface dry. Okay, the surface is still dry. There's no water on the surface, but the internal pores or permeable pores are saturated with water. Okay, as we can see, all the pores are filled with water. So this condition is the condition we want for our aggregate, but in real situation, it almost never happens. When we design a concrete, when we provide a mixed design, we provide how much aggregate we needed. And this aggregate should be in saturated surface dry condition. You may wonder why that's the case. That is because under SSD condition, the aggregate will neither absorb water or give out water to the cement paste. Okay, so that means the water to cement ratio will not change because moisture condition of the aggregate. The last moisture condition is called wet condition. All the permeable pores are saturated, and on the surface we have some water. Okay. And based on this 4 moisture condition, we can calculate absorption capacity. Okay, this is the important parameters for aggregate. That does not change depending on the moisture condition of that aggregate. So that means for a certain type of aggregate, for example, medium sand in the lab, the absorption capacity is fixed. We can measure the absorption capacity of aggregate in the lab. It is defined as WSSD, which is the weight of the aggregate in saturated surface dry condition, minus the weight of aggregate in OD, which is oven dry condition, divided by the weight of aggregate in oven dry condition. Okay, again, absorption capacity is intrinsic parameters for certain type of aggregate, does not change depending on the moisture condition. The moisture condition can change easily. Okay. We also have the so-called effective absorption, which is the difference between SSD and AD, which is air dry condition, or the surface moisture, okay, which is difference between the wet condition and SSD condition. Okay, but these two parameters are not as important as absorption capacity. Okay, again, when mixed in SSD condition, the aggregate will neither absorb or give up water to cement paste. Okay, always use SSD weight of sand and coarse aggregate in mix design calculations. Okay, so this is again very important. We'll talk about mix design, how to design the concrete in I think next week. Okay, but here remember we should adjust moisture condition of aggregate before we use it. All right. And the next slide is also very important. This shows us how to adjust the moisture condition for aggregate. So again, from mix design, we need to get the SSD weight of aggregate and how we can adjust the mixed water and the stockpile, which is the real aggregate, okay, based on daily condition. If there's rain, the moisture condition will change. You know, we have more moisture on the surface of aggregate, and we need to adjust how much stockpile aggregate we need to add it in the concrete. So let's say we have moisture content of the stockpile of aggregate. MC, which is moisture content, is the difference between the weight of stockpile aggregate minus the weight of SSD aggregate divided by weight of SSD. Okay, so moisture content is something we want to adjust moisture condition. Okay. The W stockpile is very easy to do. We just pick a certain amount and measure the weight. But the WSSD is pretty hard to measure because SSD is saturated surface dry. On the surface, it's dry, but inside is saturated. Okay, it's pretty hard to measure WSSD. Okay, instead of measuring, we can calculate that. Okay, using a second equation here. So WSSD is equal to 1 plus AC. AC is absorption capacity, which is in the previous slides. Okay, and also WOD. OD is weight of oven dry aggregate, which is much easier to measure. We take a certain amount of aggregate, we put it in the oven overnight, and then we can measure the oven dry weight. And because absorption capacity, AC is intrinsic property, does not change for certain type of aggregate. So based on AC and WOD, we can calculate WSSD. And we put WSSD into the first equation so we can calculate the moisture condition. And then we can finally do the adjustment to the mixed water. Okay. So based on the mixed design, we get W aggregate. So this is the weight of aggregate in saturated surface dry condition from mixed design. How much aggregate from stockpile we need to adjust. Okay. The moisture condition could be positive or negative. Okay. If the moisture condition is positive, that means the aggregate is wet. So water will be subtracted from mixed water. If the moisture condition is negative, the moisture condition is air dry. So water should be added to the mixed water. Okay. So I know this is very confusing. Let me show another example. Okay, so can you see my iPad? Okay, so let's see, we have designed our concrete mix. So we need 500 pounds of cement. We need 1,000 pounds of sand. Remember, the sand should be in the SSD condition based on mix design. Okay. And also we need 1,000 pounds of SSD coarse. Okay. For water, we need 600 pounds of water. Okay. And let's see, we calculate the moisture content for the sand. For the sand is plus 2%. Okay. Which means the moisture condition of sand is wet. So on the surface of the sand, we have moisture. Okay. For the coarse aggregate, we calculate the value is minus 3%. Okay. And moisture condition for the coarse will be air dry. Okay. So how we can adjust the moisture content based on this information? We need to decide how much stockpile weight for the raw materials we need. Okay. For cement is simple. Cement is always dry. We need 500. We need 500 from the bags, cement bag. Okay. For sand, we need 1,000 pounds of SSD sand. Okay. But because the sand has plus 2% of moisture, okay, the stockpile we need plus 1,000 plus times 2%, okay, which is around 20 pounds of moisture. So in the stockpile weight, we actually need 1,020 pounds of stockpile sand, of the bed sand. So we can think this 120 as 100 pounds of SSD sand, which we actually need from mix design, plus 20 pounds of actual water. So the sand can provide 20 pounds of actual water. Okay. Because we need actually only 600 pounds of water. And the sand provides 20 pounds of actual water. So the mixing water, we should minus 20 pounds. Okay, I hope that makes sense to you. Okay. For the coarse aggregate, the moisture content is minus 3%. That is air dry coarse. Okay. How much stockpile we need? We need 1,000 pounds, which is in SSD condition, and minus 1,000 times 3%. So we need 970 pounds of coarse aggregate. So this coarse aggregate again is in air dry condition. Okay, so that means to make 1,000 pounds of SSD coarse, we need 970 pounds of this air dry coarse, and plus we need 30 pounds of actual water to make it 1,000 pounds of SSD coarse. How to do that? We need to provide 30 pounds of actual water to it. So this is the stockpile weight for sand, coarse, and mixed water. Okay. Again, this is maybe confusing to us initially. Trying to understand as you could, and we're gonna talk more about it when we talk about how to design a concrete. Okay. Okay. All right. Okay. And the size and the shape of aggregate is also important. Okay. because the size will affect the workability by affecting the surface area. Okay. The smaller the particle size, we need a higher water because the surface area will be higher. Okay. Okay. Coarse aggregate is cheaper to manufacture because we do not crushing the coarse aggregate into a much finer size, as in the case of sand. Okay. The higher the maximum size, we need less cement paste, but the strength will be lower. That is because when we increase the size of coarse aggregate, the internal stress of coarse aggregate, the boundary between the coarse aggregate and cement paste will be larger. So the internal stress, the stress concentration will be higher when concrete is under tension or compression. Okay. So as a result, when everything is the same, just increase the size of coarse aggregate, the strength of concrete will be lower. Again, we're going to talk about this more when we talk about compressive stress of concrete. Okay. For size guidance, should not be larger than 1.5 inch. Okay. The nominal maximum size of coarse aggregate should be less than 90 millimeter, which is 3/4 inch for high performance concrete. Okay. It should be less than 20% of the minimum dimension of the formwork. Okay. And should be less than 3/4 inch of the spacing between the reinforced bar. Okay. Because if the size of coarse aggregate is larger than that, we may have some blockage between the reinforcement. Okay. So these are some general guidance on the size. Angular shape, rupture surface, or elongated shape of aggregate that will increase paste requirement and reduce the workability of the concrete. Okay. Organic impurities, they may reduce the strength of concrete. They may affect the chemical reaction, the hydration, increase or decrease the settling time, because some of impurities may act as retarder or accelerator. They may even interact with chemical admixtures, such as superoxidizer, accelerator, and so on, because these organic materials could easily interfere with the chemical admixtures. Many of them are also organic materials. If the materials is too fine, less than 75 micrometer or passing the number 200 sieves, they may weak the bonds between the cement paste and aggregate. So the strength of the concrete will be lower. They may also increase the water demand because the particle size is smaller, the surface area will be very high. We need much more water, so this is not desirable. Okay, so then potential alkali-silica reaction. Some of the aggregate has reactive silica, and this reactive silica may have a chemical reaction with alkalis. So this is sodium hydroxide. Na is for sodium, H is for hydroxide, K is for potassium. Okay, so NH is sodium hydroxide, KH is potassium hydroxide. Together with water, they may generate expansive alkali-silica gel. So after concrete hardens and we have this expansive gel, the concrete may break because of the tensile stress introduced by this gel. Okay, we'll talk about this more again. Okay. All right, so today we talk about water and aggregate, especially aggregate is very important. We talk about how to calculate the finest modules of aggregate, which is not hard. In lab number 3 or number 2 or number 3. So next week, we're gonna measure the finest modules of aggregate based on radiation. What are the formation conditions of aggregate? We have oven dry, air dry, SSD, or saturated surface dry, and wet condition. And most importantly, how to calculate moisture content and adjust the mixing water based on that. Okay. Okay, that's it for today's lecture. Any questions?